So section E-2 is the end behavior and horizontal or slant asymptotes of rational functions. So let's first make a note that in order to locate any horizontal or slant asymptotes, one must determine what's called the end behavior of the rational function. So let's start by making a table that we're going to complete to describe the end behavior in three different scenarios. So as we know, rational functions are written as follows here. And what we'll see is that sometimes the numerator's degree will be bigger than the denominator, sometimes they'll be equal, and sometimes it'll be less than. So we have three possible scenarios that we're going to write a different conclusion for. Now, let's say the degree of the numerator is equal to the degree of the denominator. What we do is we start by saying, alright, in this example, determine the end behavior of h of x, then plot h of x to see what this looks like graphically. So how do we start by determining the end behavior? Well, think about this. End behavior of a function really means as it goes to the end, as it gets really, really big, or as it gets really, really small. So as x goes to infinity, or as x goes to negative infinity. Now with that said, let's take a look at h of x as the absolute value of x gets larger in both directions. So as x gets bigger from 10 to 50 to 100, notice this is honing in on the number 2. And as x gets bigger in the other direction, negative 10, negative 50, negative 100, it's also honing in on 2. So what we're going to see is that absolute value of x gets larger, the value of h of x approaches 2. This is our indication of a horizontal asymptote. And we can see it right here in the graph. Okay, there's the horizontal asymptote. As the function got larger, we saw that h of x was getting smaller, closer to 2. Well, this is getting smaller and smaller and smaller, just getting closer to 2. But here it was getting larger, larger, larger as it goes to the left, but still going toward y equals 2. Now another way to look at this, although it's not mathematically sound, you could say plug in infinity into the function. Well, if you think back to the function was 6x over 3x minus 4. So if you do h of infinity, you plug infinity there and infinity there. So this infinity and this infinity are very, very large numbers. Now same thing here. 6 times negative infinity, 3 times negative infinity. We could say that this infinity is so large that this negative 4 has no significance. Because if you think about it, take triple infinity and then subtract 4 from it. It's still going to be a crazy large number. So since this plus or minus infinity is such a large value, then anything without the plus or minus infinity can be neglected or considered to be negligible. So in reality, this negative 4 doesn't matter. So we just take a look at the function like this without the negative 4. And we'll see 6 infinity over 3 infinity. If you cancel the infinities, you get 6 over 3, which is just 2. And that's exactly what our end behavior was going toward, as the height of the function was going toward 2. Okay? Again, here, the height of the function is also going toward 2, but from below. And we're going to see that right here as well. We're going to have negative 6 over negative 3, still giving us 2. Now, example 2 says determine the end behavior of g of x, still where the denominator and numerator's degrees are equivalent, just like they were before. So this is x squared, this is x squared. But now, instead of just plugging in infinity, let's take a look at this problem and see what's really going on. Now, the way to solve this one is to start by dividing by the numerator and denominator by the variable part of the term with the highest degree. So x squared is the highest degree. So let's divide the numerator and denominator by x squared. 2x squared over x squared is just 2. 4 over x squared is 4 over x squared. Then these 8x squared over x squared is 8. 5x over x squared is 5 over x. And negative 3 over x squared is negative 3 over x squared. Now let's think about what happens as x goes toward positive or negative infinity. If we plug in g of infinity into this function here, these denominators all become infinity. And when a denominator is infinity, the value of the function, or the value of that expression right here, really becomes 0. This becomes 0. This becomes 0. The reason is, think about it. If you take a pizza and divide it by 2 people, each person gets a half a pie. Then you divide it by 10 people, everybody only gets a little bit, a tenth of a pie. Then divide it by 20 people, everybody only gets a small piece. If you divide it by like 10,000 people, you're going to get like a crumb each, which is pretty much nothing. If you divide it by an infinite amount of people, technically everybody really gets nothing at all. So what we're trying to say is that when we divide by infinity, it's like the value is getting smaller and smaller and smaller. So these have no significance in the problem when you divide by infinity. So the result just becomes 2 over 8. Same thing here, 2 over 8. This drops off. Anything divided by infinity is becoming, or is a limit that goes to 0. So as a result, we get 2 over 8, and 2 over 8 is simply going to give us 1/4. Okay, this 2 over 8 right here and here gives us 0.25. Okay, but we're also going to notice here that this crosses at one point, and this shows us that asymptotes, and we're going to see soon that certain types of asymptotes can be crossed actually, but the behavior still tends toward it. So this line, or this asymptote, gets crossed, but then it goes back up toward the asymptote and rides alongside of it. So as a conclusion for this, what we'll notice is that we could really look at the ratio of the leading coefficients to determine the end behavior when the degrees are equivalent. And we could have done that in the beginning. If we looked at the leading coefficients, 2 over 8, that's 0.25. We could have done that in the last example as well, doing 6 over 3, giving us 2 as the horizontal asymptote, y equals 2. Next, let's take a look at an example when the degree of the numerator is less than the degree of the denominator. So we have 4, which has no degree to it, over x minus 1, which has a degree of 1. So clearly we're going to see here that the numerator's degree is less than the denominator's degree. So in this problem, let's go ahead and just simply plug in infinity. And we take f of infinity because we're looking at the behavior as x gets larger and larger and larger as the graph goes to the right. Well, you end up getting 4 over infinity minus 1, which is really 4 over infinity, which is just 0. And the same thing occurs here. You get 4 over negative infinity, which is still 0. Remember, anything over infinity is approximately 0. So right away we're going to see that when the degree of the numerator is less than the denominator, the behavior is that the graph tends toward y equals 0, or it tends toward the x-axis. Let's see that again in one more example here. Here we're going to have negative 5x over the quantity x squared plus 4x minus 2. And we can start by dividing the numerator and denominator by the variable part of the term in the numerator with the highest degree. So we look at the numerator for a second and we see that this x is the highest degree. So we'll divide by x and divide by x. Well, the numerator becomes negative 5. Here's the denominator. If I plug in infinity now into this function, this becomes infinity, this becomes infinity. This is 2 over infinity right here. It drops off. So you get negative 5 over infinity plus 4. But the 4 really has no significance. So in this case, again, we get a number over infinity, which is approximately 0. And the same thing occurs here. So as a conclusion, if the degree of the numerator is less than the degree of the denominator, then the function has a horizontal asymptote given by the line y equals 0, also known as the x-axis. And finally, if the degree of the numerator is greater than the degree of the denominator by 1, okay, we're looking at examples only when it's greater by 1, what happens? So we have a quadratic over a linear. So clearly this is greater than this by a degree of 1. Let's go ahead and just plug in infinity right away. Plug in infinity. If you plug in infinity here, well, the problem is that you get infinity squared over infinity, which just becomes infinity. If you plug in negative infinity, you get infinity squared over negative infinity, which just becomes negative infinity. Well, clearly we can see that as x increases, right, as it goes to infinity, the graph increases to infinity, and as x goes to negative infinity, the graph goes to negative infinity. So what we're going to see is that the value of the function doesn't converge to a certain location. So the asymptote that's associated with this rational function is called a slanted asymptote. And a slant asymptote is found by determining the quotient of the numerator and denominator either by long division or synthetic. So take the numerator and divide it by the denominator. So let's use synthetic. So this is 1, 3, negative 4. That's 1, 3, negative 4. Dividing by x plus 1 means put a negative 1 outside. Bring down the 1. This gives me negative 1 plus 3 is 2. This gives me negative 2 plus negative 4 is negative 6. So as a result, I get x plus 2 minus the quantity 6 over the quantity x plus 1. Well, if we take a look, we're trying to figure out the end behavior, which means as x goes to infinity. Well, if x went to infinity, this would put an infinity down here in the denominator for this portion, which would make the 6 over infinity, which really becomes 0. So in essence, this is the important part, not the remainder. So everything but the remainder is the important part to see the slant asymptote. So the slant asymptote here is x plus 2. And we can see that in the graph right here. This is the line x plus 2, and this is the rational function. And see how nicely the rational function tends toward it. Okay, and again, we saw that as x got bigger, y went to infinity. That's this right here. X is going to the right, while y is getting bigger and bigger. X was going to the left, y was getting smaller and smaller. So as a conclusion, if the degree of the numerator is 1 larger than the degree of the denominator, then the graph has a slant asymptote.